This presentation will cover breach, the last phase of the internal erosion process. After this presentation, you should be able to explain the breach phase of internal erosion, identify the various breach mechanisms that may occur, and assess the likelihood of breach. This presentation will provide an initial overview and will then discuss the various breach mechanisms that lead to uncontrolled release of impounded water and the conditions that drive them. Let's begin with an overview. Breach is the fourth and final phase of internal erosion. Fellatol 2015 and ICOLD Bulletin 164 refer to this phase of internal erosion as both breach initiation and breach. Breach occurs when there is uncontrolled release of impounded water through a section of the embankment in which the crest is dropped to below the impounded water level. According to FEMA 148, failure or breach is characterized by the sudden, rapid, and uncontrolled release of impounded water. FEMA P-1025 subsequently expanded the definition to include liquid-borne solids. The FEMA 148 definition is used in both the dam safety policy and levee safety policy. Dam safety tends to use failure, and levee safety tends to use breach. However, in the context of this definition, they have the same meaning and can be used interchangeably. ICOLD Bulletin 164 and Best Practices in Dam and Levee Risk Analysis describe three phases in the breach process, which are illustrated on the generic breach outflow hydrograph. These phases will be discussed on the next three slides. The terminology can lead to confusion since some of the same terms are used differently for the hydraulic model of the breach, the internal erosion of entry, and warning and evacuation timeline for LifeSim. The breach initiation phase, as defined in this figure, is not included in the hydraulic model. For HEC-RAS, breach initiation is at time t equals 0 on this hydrograph. Breach initiation in HEC-RAS is the breach event of interest for the internal erosion of entry. Beyond this time, the breach is virtually certain to form. The breach initiation phase begins with the first flow of water over or through the dam, levee, or foundation. It produces observable erosion with the potential to progress and cause failure. During the breach initiation phase, the zone of active erosion is downstream from the point of hydraulic control of the flow, so outflow rate changes only in response to changes in the driving hydraulic head, not as a result of erosion. As breach initiation proceeds, the zone of active erosion generally moves upstream via head cut or surface erosion during overtopping flow. The breach initiation phase ends when the active erosion front reaches the crest or upstream face of the dam, thereby producing a rapidly accelerating breach outflow and typically unstoppable failure of the dam or levee. The breach formation phase begins when erosion and outflow begin to increase rapidly, often due to a head cut reaching the upstream side of the embankment or a piping roof collapsing. During this rapid downcutting phase, the breach widens and deepens quickly. It ends when flows begin to level off and the peak flow has been released. It is unlikely that outflow and failure can be stopped. In the final phase, the breach has usually reached its full depth and continues to widen as long as the driving hydraulic head is available. Widening is accomplished through a combination of foundation and structure erosion and stability failures, which includes episodic mass wasting of material from the banks of the developing breach. The widening can be stopped either by exhaustion of the headwater or raising of the tailwater that reduces breach inflow to non-erosive velocities. In some levee systems, widening can continue for days or months until flows subside or the breach is repaired. The end breach time in the HEC-RAS model can occur before the true end of the breach widening phase. The hydraulic model typically only cares about the main part of the formation and widening phase. If a breach initiates due to internal erosion, it usually leads to breach formation. Breach is almost certain to occur if a continuing erosion condition is expected for the filters or transitions, or there are no filters, and detection and intervention have failed. Exceptions include the water level dropping below the inlet of the developing pipe before a breach mechanism has time to develop, and large freeboard relative to the expected deformation. For event tree analysis, the breach event must be clearly defined and understood by the team. If breach occurs, the full breach parameters and consequence modeled are realized. In addition, the breach characteristics used in the hydraulic and consequence modeling must be consistent with the breach event for which the likelihood of occurrence was estimated. The uncontrolled release from the event must be enough to matter with respect to incremental consequences due to breach. Breach mechanisms. Fell and Fry 2007 schematically showed 4 breach mechanisms associated with internal erosion. These include gross enlargement of a pipe or concentrated leak, as shown in the upper left, overtopping due to crest settlement or sinkhole development, shown in the lower left, sloughing or unraveling of the downstream face, the lower right, and slope instability in the upper right. For most embankment types and potential failure modes, the likelihood of breach development will be dominated by 1 or 2 of the potential breach mechanisms. Most will eventually lead to overtopping. Gross enlargement of a pipe or leak requires a continuing erosion condition with no self-healing. The process can only stop if the water level drops below the inlet of the developing pipe before breach occurs, or the water level drops sufficiently to reduce the hydraulic shear stress below the critical value. The photographs on the right are from the ARS field testing. The videos were previously shown during the erodibility parameters presentation. As the breach progresses and the reservoir drains, the roof of the internal erosion pipe will collapse. Dam break analysis typically assumes the piping roof collapses when one of 2 conditions occur. Erosion of the roof reaches the embankment crest profile, or free surface flow along the entire conduit length and the pipe diameter or width is more than twice the vertical overburden height, the vertical distance from crest to roof. The latter is illustrated by the figure on the lower right from the WinDam-C software documentation. The breach process for overtopping and internal erosion are described by Bruner 2014 as it relates to dam break modeling using HEC-RAS. The figure on the left is for an overtopping failure. Overtopping erosion and head cutting will begin to occur on the downstream side and progress through the crest. A similar process is observed locally with piping failures and globally at the advanced stages when overtopping is common. The figure on the right is for a piping failure. During the piping flow process, erosion and head cutting will begin to occur on the downstream side as a result of flow exiting the pipe. As the piping hole grows larger, material above the hole will begin to slough off and fall into the moving water. Head cutting and material sloughing processes will continue to move back towards the upstream side while the piping hole continues to grow simultaneously. This is a video of a large-scale field test of a dike in the Netherlands. Small head cuts can initially form at the discharge end of the pipe, leading to bigger head cuts when the crest collapses and overtopping ensues. This is not visible in the video, but is shown in the figure at the bottom right. Here is a better look at the extents of the large-scale test. At this point, the crest is lowered with the embankment collapse into the developing pipe. The freeboard is then exceeded on the deformed crest overlying the pipe, and overtopping ensues. Here, a couple of head cuts are observable as overtopping erosion continues. Multiple head cuts appear to have now merged into one larger head cut. And here's the final breach width at the end of the video. Overtopping is the second internal erosion breach mechanism. In this example, fines are removed from a zone of internally unstable material in the embankment by suffusion, and the overlying fines move into the remnant open work zone by internal migration, leading to crest settlement large enough to result in overtopping. Alternatively, subfosion can occur in a zone of internally unstable material in the embankment, resulting in settlement that leads to overtopping. As previously mentioned, most breach mechanisms will eventually lead to overtopping. Overtopping can also occur due to sinkhole development. Internal migration of embankment and/or foundation materials into open defects leads to stoping and development of a sinkhole or depression in the crest that drops below the water level. An open rock defect is illustrated in this figure, but as previously discussed, open defects can also occur with embedded structures such as conduits, pipes, or culverts. Where the sinkhole develops is critical along with the water level at the time of occurrence. In this first example, a sinkhole at the crest is large enough to lower the crest, leading to overtopping. If the sinkhole develops at the downstream toe, it must lead to progressive slope instability and eventually overtopping. The event tree may need to consider the sinkhole location, if not well defined by the site characterization, and understanding of the foundation geology. For conduits, pipes, or culverts, the location could be informed by video inspection results. These photos are from the Corps of Engineers Clearwater Dam in Missouri in 2003. A 10-foot wide and 10-foot deep sinkhole formed on the upstream face at elevation 570, following the record pool of elevation 568. It took about 2 weeks for the reservoir to recede to elevation 560, and it took about 2.5 months to recede back to normal levels. The sinkhole was probably the result of long-term, intermittent internal migration of shell and natural alluvial material into the karst foundation, and more intense internal migration when the reservoir was high. Sloughing is the third internal erosion breach mechanism. For sloughing to occur, the downstream face would have to be relatively steep, and the downstream shell would have to be comprised of cohesionless soil, probably sandy gravel or gravelly sand, possibly with some silty fines. Increased seepage would have to discharge into the downstream shell, as shown in the cross-section at the bottom left, for a concentrated leak in the core of a zoned embankment, or as shown in the cross-section at the bottom middle for internal erosion in the foundation. The oversteepening and progressive slumping process would have to be allowed to continue until it gradually eroded away the crest and allowed the reservoir to overtop the embankment. Sloughing is a slowly developing breach mechanism, which should take days or weeks to lead to breach. The figure on the right illustrates progressive sloughing that occurs in a homogeneous embankment due to through seepage. These figures show sloughing due to seepage through sand levees with steep slopes. Sand levees without a waterside impervious layer reach steady-state conditions rapidly and are prone to through seepage. Seepage exiting on the landside slope would result in high seepage forces, decreasing the stability of the slope. Through seepage has been successfully mitigated for these levees by using sufficiently wide levee sections with flat slopes, although these slopes do require maintenance during high water events. For example, there are many miles of sand levees in the Mississippi River Valley with 5-to-1 landside slopes and 4-to-1 waterside slopes. Reclamation's Fontenelle Dam in Wyoming nearly breached by sloughing, but the breach process occurred slowly enough so that the reservoir water surface was able to be lowered over the span of several days and arrest the breach. A sinkhole also developed on the crest, and there may have been piping along the soil-rock interface as well. Unraveling refers to progressive removal of individual rocks by large seepage or leakage flows through a downstream rockfill zone. In reality, rockfill has a large discharge capacity, and a number of dams have survived flows greater than 1 cubic meter per second. Here's an example of a dam that survived large seepage flows. Construction on the 300-foot-high concrete-faced rockfill dam on the Tokwe River in Zimbabwe began in 1989. The upstream face was being prepared for the concrete facing to be placed last. Extreme flooding occurred when the rockfill embankment was 60% complete, a height of about 200 feet. The water level rose to within 5 feet of the existing crest. Floodwaters passed through the dam for 2 weeks without failure. The downstream rockfill slopes unraveled locally. However, construction of the rockfill continued throughout flood conditions, and as the flood receded, the rockfill was restored and repaired. Suffusion of the finer fraction of internally unstable downstream shells can increase the permeability, which can lead to sloughing and unraveling of the downstream or landside face. The likelihood of breach due to unraveling can be informed by assessing the rock size to withstand a unit discharge through the rockfill as a function of slope and unit discharge using the methods of Slovic 1991 and Olivier 1967 and the revised method of EBL 2005 as shown in the figure on the right. It is suggested to use the EBL 2005 method because the Slovic and Olivier method is too conservative. In the example shown, for a given discharge of 0.3 cubic meters per second per meter, the mean rock size for stability is about 3 times as much for the Slovic-Olivier method than the EBL 2005 method. Stability of the discharge face of an unreinforced rockfill slope depends in varying degree on these characteristics and conditions listed in order of increasing importance: specific gravity of the rock particles, dominant particle size of the rockfill, gradation in shape of the rockfill particles, relative density of the rockfill, rate of discharge, maximum gradient, and inclination of the downstream slope of rockfill. The fourth and final internal erosion breach mechanism is slope instability. Internal erosion could cause high pore pressures in the foundation or embankment, resulting in reduced shear strength and slope failure. Breach could occur if the failure surface or progressive instability without intervention intersects the water surface or slope deformations are significant enough that the remnant slope cannot resist water load. Although it is possible, this is generally not considered to be a very likely breach mechanism for most dams. No historical failures from slope instability due to increased pore pressures in the downstream slope are known to exist, and a unique set of circumstances would need to exist for it to be a major concern. Conditions making this breach mechanism more and less likely to occur are shown on these two cross-sections. This table summarizes the potential breach mechanisms based on embankment dam zoning. Some breach mechanisms will not be applicable to some embankment zoning types or potential failure modes. This table applies to internal erosion due to a crack or gap in the embankment from differential settlement, hydraulic fracturing, poorly compacted layer, or climatic conditions like desiccation or freezing, and internal erosion in a soil foundation. This table does not apply to potential failure modes involving open or infill defects and solution features in rock foundations because the leakage flows may exceed the capacity of even free draining rock fill. In summary, all four breach mechanisms lead to crest settlement and overtopping erosion. One or more of the mechanisms may occur during the breach process, and it is generally not necessary to know precisely which mechanism or mechanisms would occur. Gross enlargement of a pipe, or concentrated leak followed by collapse of the embankment, loss of freeboard, and overtopping is the most common mechanism. The following table from the Best Practices Manual can be used to help assess the likelihood of breach. It can be used as a starting point, but the risk team must develop project-specific more likely and less likely factors to guide subjective probability estimation. The factors in this portion of the table address breach by gross enlargement of a pipe or erosion pathway. The factors in this portion of the table address breach by sloughing and unraveling. The factors in this portion of the table address breach by slope instability. And and the factors in this portion of the table address breach by sinkhole development. Next, we'll go through a quick overview of the breach toolbox. The breach toolbox includes worksheets for each of the different breach mechanisms. The primary references used to develop this presentation are shown here. This concludes the presentation on breach, the final phase of the internal erosion process.